All right, welcome back. So I see that I've scared a few people off, which is good because now things are going to get technical. So let X be a Banach space. Okay. All right, so there are lots of matrix concentration inequalities. So you can do Bernstein with unbounded random matrices, for example. There are matrix series bounds, which we'll talk about in a minute. There are matrix Chernoff bounds. There are matrix Azuma bounds. Anyway, basically, take every one of your favorite concentration inequalities and put matrix in front, and there might be a version. So all these things you do in the scalar setting can be transported to the matrix setting by sticking matrix in front, usually with a much harder proof. And so this really is a pretty extensive toolbox. So what we're going to do the next 2 hours is talk about two methods that can be used to establish these types of results. Normally, like I said in these tutorials, what I would do is repeat what I just did 5 more times. Here's a matrix. You can write it as an independent sum. Here's a concentration inequality that you can apply to that sum. Here's what happens when you compute the variance. So you don't want to watch this. But it's in the notes if you're interested in these examples. So what we're going to do first is I'm going to show you how to prove a tail bound for matrix Rademacher series. I'll tell you what that is in case it's not clear. And the method of proof is the Laplace Transform method, which is the simplest way to prove scalar concentration inequalities, plus a very deep result from matrix analysis called Lieb's theorem. So that's going to be the topic of this lecture. So I'm going to show you one of the successful methods for proving matrix concentration results. And then in the third lecture, for those of you who survive, we're going to prove a moment bound for a matrix Rademacher series. And the approach here, so this is called the non-commutative Khinchin inequality, or the matrix Khinchin inequality. Some of you may have heard of this before. We're going to prove this using Stein's method. So a very, very different kind of technique. And this is the simplest proof I know for this result. It's extremely powerful. And even in the scalar setting, these results are not necessarily so easy to prove. So this is a really slick way to get a lot of juice. Okay, so here's what we're going to be doing. I'm going to start with the scalar case, just to remind you how this stuff goes, and then I'll show you how it extends to the matrix setting. So most of the work in this lecture is from a paper I wrote called User-Friendly Tail Bounds. That appeared in FOCM in 2012, Foundation of Computational Math. Okay, so all of this stuff that I'm telling you about is based on a principle that I think we can safely attribute to Alsveda and Winter. And that principle comes from a paper about something that doesn't seem like it has much to do with random matrices. So Alsveda and Winter are information theorists, and they're interested in the capacity of quantum channels. And to analyze these things, they had recourse to study a certain kind of random matrix. And so somewhere buried in the back of their paper, they're like, we thought these tools might have some additional application or use, so we thought we'd write all of this stuff out. And in the back of the paper, they prove a very simple version of the matrix Chernoff inequality. And what I really think is powerful about their paper is not so much the particulars of their proof, but the idea that we can prove matrix concentration inequalities by lifting scalar concentration inequalities. And in fact, we can lift the arguments. And to make this work, you need a lot more machinery. You'll see part of the reason why this is true. But this has actually been a very successful principle. And both of the results I'm going to tell you about follow from the same template. And this is really an idea that I think we can attribute to these guys, because this is exactly what they did in their paper. OK, so what is a Rademacher series? This is the object we're going to be studying for the rest of the afternoon. So a scalar Rademacher series has two pieces. So we need some coefficients. So we're going to let a1 up to an be real numbers. These are fixed. And we need some randomness because we're talking about probability. So we'll let epsilon 1 up to epsilon n be IID Rademacher variables, which is to say uniform on plus minus 1. So we often call these guys Rademacher random variables, and I'm going to follow that convention. So independent, identically distributed random signs. And we're interested in the random matrix X, which is given by modulating these scalar coefficients by random signs and adding them up. OK, so you might be interested in the tail behavior of this kind of random variable. So what's the probability that x exceeds some level t? So I'll prove this result for you in a minute, but it's pretty well known that this type of random variable has a tail bound of this form. It looks like a Gaussian. And the variance is just the expectation of x squared, which you can easily compute as the L2 norm of the sequence of coefficients. Okay? So the L2 norm of the sequence of coefficients is, in fact, the variance of this random variable, and it controls the moderate and large deviations of this random variable. And Cramé's theorem will tell you that, in fact, this estimate is more or less sharp asymptotically. OK, so this is a good bound. And it says that this random variable looks like a Gaussian. So centered around 0. And the width of the lobe is roughly 0, roughly sigma in each direction. OK, now, what's a matrix Rademacher series? So it's a simple extension, but instead of scalar coefficients, we're going to have some matrix coefficients. So we're going to let a1 up to an be d by d Hermitian matrices. Okay, so Hermitian means conjugate symmetric. If you prefer, just think symmetric. Now, the thing about a Hermitian matrix, as you may learn in an operator theory class, is it's really the matrix equivalent of a real number. Okay? So just like a real number is equal to its conjugate, a Hermitian matrix is equal to its conjugate transpose. And Hermitian matrices actually behave a lot like real numbers, which is maybe a little bit surprising, but with the right tools from operator theory, you can really push through this insight. Okay, so once again, we're going to need some randomness. So we'll let epsilon 1 up to epsilon n be IID Rademachers. So these are scalars still. And we are going to make a random matrix X by modulating these matrix coefficients by these random variables and adding them up. So flip the sign of each matrix, add them up, see what happens. Okay, so we'd like to understand how big X is. We'd like to know the probability that it exceeds some level. And we'd like something here on the right. Now, there's a problem. What does big mean when we're talking about a matrix? So we're going to measure the size in terms of the maximum eigenvalue. So the algebraic largest eigenvalue. We'd like to know the probability that it exceeds some level t. We'd like to fill this in. And
the AI have to be mean zero, right?
No, the AI are not random.
The mean comes from the epsilon.
Yeah, the mean come from the epsilons. Okay, so we'd like to fill in this blank here. And what I'm going to argue is that the method we use to prove this result has a direct extension that lets us prove a result of this form. For the moment, I'm going to leave you in suspense about what belongs in the blank. So let me remind you about how you prove that sub-Gaussian bound for a Rademacher series in the scalar case. I'm going to go through this quickly because I expect most of you have seen this at some point in your lives or have taught this at some point in your lives. So okay, so the first thing we're going to do is apply what's called the Laplace Transform method. So this is often known as Chernoff bounding or Hoofding bounding. Really, it goes back to Bernstein in the 1920s. I've been chastised for saying that, but it really is a very old technique from the Russian literature. So we're going to be interested in the probability that this Rademacher series in the scalar case exceeds a level t. And the way that we're going to deal with this is by fixing a scalar parameter theta, which is strictly positive. We're going to multiply both sides of this event by theta. Doesn't change the event. And then we're going to exponentiate. The exponential is monotone, so it doesn't change the event. So this is equal to the probability that the exponential of theta times epsilon k ak is greater than e to the theta t. It's the same event, same probability. All right. Now, we're going to apply Markov's inequality to this non-negative random variable. So Markov's inequality tells us that the probability is bounded by the reciprocal of the level, so e to the minus theta t, times the expectation of the random variable. Okay, so that's step one. This is the integral of an exponential with a parameter in it, which is the reason for the name Laplace transform. Okay. Now, we need to stare at this thing. Okay. So what's this object called? This is called a moment generating function of the sum x. Now, x is the sum of independent variables, and what we're going to need to show is that the moment generating function of the sum is the product of MGFs. So the second step is to show that the MGF of a sum, of an independent sum, equals the product of the MGFs, of the summands. So this is really easy because of independent. Can't keep track of these erasers. All right, so what do we do? So the expectation of a sum of independent variables, well, the exponential of a sum is always equal to the product of the exponentials. And by independence, we can swap the product and the expectation. And what we have here now is the MGF of each summand. Okay? So we have an MGF of the sum, and we have an MGF of the summand. So now, if we want to continue, we need to bound this moment generating function. Okay. So let's have a look at this guy. So this is a Rademacher times a parameter theta times a number a. So Rademacher takes two different values, +1, -1 with equal probability. So this is equal to 1/2 times e to the plus theta a plus 1/2 times e to the minus theta a, corresponding to the two values of epsilon. So this look familiar? This has got a name. It's the hyperbolic cosine of theta a. And I'm cleverly going to bound this by the exponential of theta squared over 2 times a squared. So to know that this is the right bound, it helps to fiddle around for a while. Okay, so we've bounded each one of the MGFs. We can introduce this back in here. And we'll obtain, so now we can complete the argument. So the probability that the sum is greater than t is less than or equal to e to the minus theta t times the product of e to the theta squared over 2 times ak squared. So we've plugged this bound into here, plug that into there. And now we pull the product back into the exponential. We obtain e to the minus theta t times the exponential of theta squared over 2 times the sum of ak squared. And this is the number that we were calling sigma squared before, the variance of the sum. And now, what's the last step? So theta's at our disposal, so we can optimize with respect to theta. And when we do that, we'll obtain the probability of the Rademacher series exceeding the level t is less than or equal to e to the minus t squared over 2 sigma squared, where sigma squared is equal to the sum of ak squared. Okay, so yes?
Quick question, is that an exact inequality or the higher order terms here? The hyperbolic cosine?
This is an identity, this is a bound. And you can get this by comparing Taylor series. Yeah, so you can check that the first derivatives match at 0. Yeah. It's really just a clever choice to make this work out neatly. You can actually finish the proof with a hyperbolic cosine and you get an even better bound, but it's hard to understand. So this one makes it very clear that this ought to have this Gaussian, sub-Gaussian behavior. Okay, so this is just a reminder of how we do things in the scalar case. And now I'm going to try and do the same thing for matrices. Okay, so here's our setup. Now X is a random matrix. We're interested in filling in this blank here. And we're going to try and do that by following the same steps on the far side of the board. So let's erase what needs to be erased.
I thought you would erase the small a's and replace them by big a's.
I am, but it's easier just to rewrite the whole thing. So proof by capitalization. Okay, so the probability that the maximum eigenvalue of this random matrix X exceeds t, well, let's multiply both sides by theta and exponentiate, just like we did a minute ago. The probability that e to the theta lambda max x is greater than e to the theta t is exactly the same event. So probability is the same. Now we're going to apply Markov's inequality. And we reciprocate the level, and we have the expectation of e to the theta, lambda max of x. And this is exactly what we did before. Now we're going to do something else. Okay. I don't like this maximum eigenvalue because it's hard to deal with. So the first thing I'm going to do is draw the maximum eigenvalue out of the exponential. So you can certainly move theta inside because it's a positive number, and the maximum eigenvalue is positive homogeneous. And the spectral mapping theorem tells us that the exponential of the maximum eigenvalue is equal to the maximum eigenvalue of the exponential. Okay? So this is equal to e to the minus theta t times maximum eigenvalue of e to the theta times x. And this is defined, for example, via power series, just like you do in your differential equations class. And if you want to get fancy, you write spectral mapping theorem in the margin. Now, we're going to do one more thing that seems kind of counterintuitive because it seems like a terrible thing to do. The exponential of a Hermitian matrix is positive because it takes all of the eigenvalues and makes them positive numbers. This is a positive definite matrix. The maximum eigenvalue of a positive definite matrix is dominated by the trace, so the sum of the eigenvalues. So we're going to make this change to get rid of the maximum eigenvalue entirely because, like I said, I really don't like this maximum eigenvalue. It's kind of a nightmare to deal with. Okay. Now it seems like this is a terrible estimate. You can also start to see where that dimensional factor is coming from in these matrix bounds. It turns out that you're not actually losing very much here, and what you gain is access to the miraculous properties of the trace, or more precisely, the trace exponential. Okay, so just carry this eraser around. Okay. Now, we'd like to continue our calculation by converting the moment generating function of the sum into the product of the moment generating functions. But now we're in trouble. Oh, I should also add before I forget that in the matrix setting, this argument is due to Oliveira. He was the one who identified that you could use the spectral mapping theorem and apply this direct argument here.
So in some sense, you're just proving the trace of the x.
Yep. Well, no, you're not, because because you can't pass the trace through the exponential. You got to determine it when you do that. So you need to do it in this order. Yeah, you got to do it in this order. And that's why the loss is so small. Yes, Sebastian?
I was just wondering, what is the spectral mapping theorem? Just by definition.
Requires some argument, but
The definition, you just diagonalize and you apply the exponential of the
Yep.
diagonal.
yeah. Like I said, if you want to get fancy, okay. I'm just showing off, Okay. So now we'd really like to argue that the MGF of a sum is equal to the product of MGFs. And now we're in trouble. Okay? So let's see what happens here. So in the scalar case, the first thing we did, we used the fact that the exponential of a sum is equal to the exponential of a product. Is this true for matrices? Epic failure. In fact, this is never true for symmetric matrices unless they commute. Okay? So this could not be farther from the truth. All right. Now, it turns out that there's a limited substitute. So if you stick a trace in front, we got a trace here, right? So it's not like we really need the raw exponentials here. So how does this compare with the trace of e to the a times e to the b? Well, it turns out that this is larger than this, always. And this is a result from statistical physics called the Golden-Thompson inequality. dates back to around 1965. And this is the approach that Alsveda and Winter used to continue the argument. But there's a difficulty here, which is that we actually have a sum of a bunch of matrices, and we'd like to compare that in some sense with the exponentials of the individual summands. Is there any relation between these two quantities? Obviously, I mean, the answer is no. Okay, so you stare at this for a minute. There's an example involving Pauli spin matrices or something like that. To show that this is not true in general. But when you stare at this for a minute, it starts to become clear why this is the wrong way to think about this problem. So if you multiply 3 positive definite matrices together, is the result symmetric? So no, not symmetric even, let alone positive. I mean, the trace could be complex. I mean, you could try and fix that by putting on an absolute value or something like that. But you see, the trouble is that multiplying matrices together destroys the spectral properties of the product. I mean, so the product doesn't really inherit all that much from the individual guys. And that's why you run into trouble here. So we need to do something else. Okay. So Alsveda and Winter used this approach in a very clever way to finish the proof. Oliveira used this in an even more clever way to establish his results. I'm going to do something different. So at this point, you scratch your head and you go to the library for 2 or 3 months, and eventually you emerge coughing from the dust. And you realize that maybe you shouldn't be working with the moment generating function. We're going to use the cumulant generating function instead. Okay, so what's a cumulant generating? It's just the log of the moment generating function. And the interesting thing is that in the scalar setting, if you take the log of the moment generating function of an independent sum, this is equal to the sum of the logarithms of the moment generating functions of the summands. Oh, I should put thetas in here. So in the scalar case, just by taking the logarithm of the calculation we made before, we see that the cumulant generating function of an independent sum is the sum of the cumulant generating functions. So CGF of independent sum, sum of CGFs. All right. Now, this looks more promising for matrices, doesn't it? Because what happens when you add symmetric matrices together? Oh, they're still symmetric. All right. And this is what we're going to take advantage of. This is not true, by the way, in the matrix case. So you have to do more work. So this is what's going on in the library for all of those months, trying to figure out what you're going to do instead. And eventually, you come across another result. So here's what we're going to do. So in 1973, Elliot Lieb was studying the problem of the stability of matter. So why it is that lots of quantum systems have nice bulk behavior. And along the way to this, he proved the following theorem. So let H be Hermitian. Then the map from A to the trace exponential of H plus log A is concave on the positive definite cone. So this takes a positive definite matrix A and spits out a number, and on the collection of positive definite matrices, this function is concave, obviously. So what happens if this is a scalar? Well, this is just A times the exponential of H. It's linear in A. All right? So there's something new happening with matrices that wasn't happening with scalars. And Lieb had the deep insight to understand that this was the case and to establish this theorem. So what does this have to do with our problem? Well, it turns out this result has probabilistic content. And that was the insight that I had after all of those months in the library. So we're going to let H be a fixed Hermitian matrix. And we're going to let X be random Hermitian. And what we're interested in doing is computing things that look like the expectation of the trace of e to the h plus x. Because, you know, we've got a sum of a whole bunch of random matrices here. And so we'd like to break that sum down.
When you say random Hermitian, you mean?
Sir?
And when you say random Hermitian, what do you mean?
So X is any distribution over the Hermitian matrices whatsoever. So it turns out that this is less than the trace of the exponential of h plus log expectation of e to the x. All right, why is that? One word? One word? Jensen. All right, so all we did here is we wrote x as log of e to the x, and we applied Jensen's inequality. That's it. But now, what do we have here? Oh, it's our friend the cumulant generating function. Aha. Okay. Any questions on what we've just done here? This is the technical kernel of this proof.
So how did you get this corollary from the previous theorem?
Okay. We write x equals log e to the x, and then using Jensen's inequality, we pull the expectation inside the concave function. Okay. That's all. This is really like a one-line argument. In one of the papers, I wrote this out, and the referee chastised me for including the details. So
can you just remind me how do we define the log of a matrix?
So for example, you can diagonalize it and take the log of each eigenvalue.
And it's PSD.
If it's positive definite. Yeah. Maybe a better way for our purposes is the functional inverse of the exponential. Okay. Any other questions on this? Sir.
Isn't that sort of almost the same as the trace of e to the a plus b, less than or equal to the trace of e to the a times the trace of e to the b?
This is a stronger result. I think I have to think about that.
Here you're taking the average of many matrices, right? Excess can take many values, many possible.
But it's just
Well, I mean, they are related. I mean, you can use similar ideas to prove a version of the a strengthened version of the Golden-Thompson inequality, but somehow, like, if you want to think about this probabilistically, you really want to think about cumulant generating functions here. Somehow they're sort of the right conceptual framework for this. And so by iterating this approach...
Is Golden-Thompson, is there something really serious, or it's just something... there is an expression that corrects the first non-equality.
Yeah, the Baker-Campbell-Hausdorff identity. Yeah, so what happens is there's another term involving commutators, and then the series will continue. I haven't seen any applications of that idea, although it seems plausible that that you could push that through. I mean, it's just that the identities are very complicated, and people usually don't even write them out beyond the second term. Yeah.
Do you know how you prove Lieb's theorem?
I do.
Is there, how do you do it?
Can we talk about that a little later?
Yes. And then just another question. So if I replace H by A, then this is the quantum entropy of A, right?
No.
A and log A commute, and then I just have
Oh,
log of A times exponential of A.
It's the entropy of e to the a.
Uh-huh. Yes, correct.
I agree.
Yes, and then, so can you relate that to the strong convexity?
Yes,
The quantum? Okay.
that's how you prove this. I'll tell you more later if you'd like. All right, any other questions on this? Okay, what are we going to do? We're going to iterate this argument. So now, if you've got the trace of e to the sum of, say, theta epsilon k ak, by repeatedly applying this result, we will obtain the trace exponential of the sum of the logarithm of the expectation of e to the theta epsilon k ak. All right. So all we did was peel the terms off this sum one at a time using this result, and we use independence to note that with respect to the randomness in each summand, the rest of the terms are fixed. Okay, so we used independence in a very strong way here. Okay, so we computed this expectation as an iterated expectation, peeling the terms off one at a time, and we used independence to do that. So it plays a big role here. But this is the matrix extension of that result. Okay, so this is the matrix CGF of a sum, and this is the sum of matrix CGFs. All right, so the next step in the argument is to figure out what these CGFs look like. So step 3, CGF bounds. So let's have a look. So we've got a fixed matrix A, a number theta, and a Rademacher variable. So let's compute the expectation. Well, this takes values plus minus 1, and we just with equal probability. So we get 1/2 e to the theta A plus 1/2 e to the minus theta A. This is also known as the hyperbolic cosine of theta A. And by diagonalizing this matrix, we obtain an upper bound of e to the theta squared over 2 times A in the semi-definite order. Okay. Same inequalities before applied to the eigenvalues. And this is a semi-definite inequality. All right. Now, we can take logarithms of both sides.
In the scalar, we also squared the A, didn't
You're absolutely right. I'm really, really bad at arithmetic. Okay. So, I'm also really bad at keeping track of the top of this marker. Okay, so we take the logarithm, and we wind up with this semi-definite bound for the CGF. By the way, you need some machinery to do this. So the log is operator monotone. So just so you understand that this is requires some attention. Okay. Now, we've got a bound for the CGF. It turns out the trace exponential is also monotone with respect to the semi-definite order. And so we can complete this bound by plugging in these estimates here. So we get the trace exponential of the sum of AK squared. Now, you can see this thing here, this matrix, as the expectation of X, this random matrix formed by summing up the AK with Rademacher variables. So this is the expectation of X squared. This is like a variance. But now it's a matrix and not a scalar. Okay? So to finish the proof, we're going to take this estimate and plug it in to this calculation here. So continuing, we have e to the minus theta t times the trace exponential of theta squared over 2 times expectation of x squared. Now, we don't like this trace anymore. We want to get back to some eigenvalues. So we're going to bound the trace by the maximum eigenvalue times the dimension.
What's t?
Sir?
What's t?
T is the level.
Oh, the,
Yeah, I'm continuing this calculation, not that one. Okay, so we've just taken this estimate here, and we've introduced it into the last line of the Laplace transform result. Okay, so now we're finishing up. So this is dominated by e to the minus theta t times d times lambda max of the exponential of theta squared over 2. All right, now we're going to apply the spectral mapping theorem in reverse. So we're going to pull the maximum eigenvalue inside the exponential, inside the theta squared over 2, until it lands on this. So all right, now we're going to call this guy sigma squared. It's just sort of the variance of the random matrix. And we're going to minimize over theta greater than 0, and we'll obtain the bound d times the exponential of minus t squared over 2 sigma squared, where sigma squared equals lambda max of expectation x squared. And this is our matrix extension of the tail bound for a scalar Rademacher series. Everything's exactly the same except for the dimensional factor, which is necessary in some cases. So there are examples where that dimensional factor really should be present in the tail bound. Now, what this tells you is that the maximum eigenvalue, you don't get any information about it up until a certain level, and then you see that the tail decays. So, and that level is lambda max of expectation x squared to the 1/2. Nope, that's not right. Okay, sorry. Maybe I'll draw this on another board. So the impact, the content of this result is that if you want to plot the probability that lambda max of this Rademacher series exceeds t as a function of t, the bound is vacuous up until a certain point, and then it drops off exponentially. So the point where the bound starts becoming informative is root 2 sigma squared log d, and then after that the scale for the deviations is sigma. Okay. Now, what if d were equal to 1? We were in the scalar setting. Oh, this would be exactly the result we got the first time for scalars. So we didn't lose anything. But again, in the matrix setting, we really do have to eat the dimensional factor for some examples. Unfortunately, this method can't tell you which ones. Any questions about this result?
so can you elaborate a little bit on because obviously, as you said yourself, you lost quite a bit moving from the largest eigenvalue to the whole trace. So cases where you do need the d would be quite mysterious. Well, the rest of the eigenvalues are negligible. What happens to them?
Yeah, that seems to be what happens. So Examples where you need this, diagonal matrices, you'll actually see this kind of behavior. It comes from the central limit theorem. In that case, this comes up for certain kinds of sampling problems. It comes up if you apply this to like a Toeplitz matrix with random plus minus ones on the first and last row. Its maximum eigenvalue has a log in it. So there are lots and lots of cases where somehow you really do have to pay for the logarithm. It's not just trivial stuff. But there are other cases where the log just doesn't belong, and this method won't tell you that.
So you actually know, the log I understand, but do you actually know cases where you, if the d would be replaced by d to 1/10, then it would be almost, you would almost feel it because it's the same log. So I wonder if there are cases where you actually lose the whole d.
You do. This bound is sharp. And you can actually find examples that saturate it, where like this really is the right estimate. So, so in spite of the fact that you feel like this was a really bad mistake, it wasn't so bad. And by the way, this really is the right scale for these series. So it's not hard to check that that sigma squared is less than or equal to the expectation of x squared is always so this bound tells you that this bound is the upper bound here. Okay, the lower bound follows from Jensen's inequality. Okay, so the gap really is just the logarithm. You really are not going to be able to escape from that sigma squared no matter what you do. So this really is identifying the sort of most significant component of the behavior.
John, you said this is for diagonal matrices. This is the log. This is accurate for...
Yeah, for diagonal matrices, you can basically make Gaussians on the diagonal, and you'll see a logarithm because of the central limit theorem.
So is this just
because you get the maximum of d
so it's like a union.
Gaussian.
It's almost
Yep.
like a union.
Yep.
bound.
It's like a union bound.
The step with the log being operator monotone, does this need some lower bound on the
No.
matrix?
No, the log is always operator monotone. This is a scalar result, or not a scalar result, it's a deterministic result. So it holds for any positive matrix, of which the exponential is 1.
Right.
Yes.
Is it possible to replace the d by some other...
It is. You can replace the d by something that's called the intrinsic dimension. So you can replace d by something that looks like the trace of the expectation squared divided by the norm of the expectation of the square. This is never bigger than d. Sometimes it's a lot smaller, but it doesn't really solve the problem of getting rid of the dimensional dependence. So
could I, for example, also take higher powers?
here, not on this result.
Because you can imagine if the eigenvalue
Sure.
became...
Sure.
You gain over L squared of inter, you gain a lot if the eigenvalues of the things you add are orthogonal to each other, isn't it? Or
Yes. So I can. This is actually a good. This is a good place to describe the difference. So, and there's one other technical point that I'd like to include before we wrap up this time. So, what's the difference between the Salzwedel-Winter stuff and what we're doing here? So. Okay, so the bound that we got here has sigma squared equal to the sum of the expectations of the terms epsilon k ak squared, which is, of course, just sum of ak squared in norm. Okay, so this is what we got. Alsveda and Winter have this bound. Okay, so they have the same estimate, except sigma squared is replaced by this quantity. So you've drawn the sum outside of the norm, and so you can see there's a huge difference between these in general. It can be as much as the dimension of the matrix. So when these guys commute with each other, not a big deal. When they don't commute, you can really lose a lot. So somehow a measure of how similar the AK are with each other. Or is that right?
Yeah, when they commute, they're equal. I mean, when they're
Yeah.
the same, they're equal.
Yeah.
So
I think that's right. Yes.
Question about Roberto's group. Did you use also Lewis theorem?
Did whom?
Oliveira.
Oliveira did not. He used the Golden-Thomson inequality in a really insightful way. As did Alsven and Winter, for that matter. It's just that somehow if you want this, the full strength of this bound, it seems like you really need to mimic the accumulant generating function argument from the scalar case. Now, one other point here. So, was there anything really special about that accumulant generating function bound we proved? Where we said, oh, what's the moment generating function of a Rademacher times a fixed matrix? Well, we found a bound for that, but you can prove all sorts of other CGF bounds exactly the same way, and you can get things like Chernoff inequalities. You can prove the Bernstein inequality this way. You can do all sorts of other stuff by mimicking this argument. This is just the simplest example. Okay, there's one more thing I want to tell you before we wrap up for this hour, and that's what you do with rectangular matrices. It seems like that's a different problem, but it's not. So we'll define a map H that takes a matrix, a general matrix B to the following somewhat larger matrix. Okay? Now, this is obviously Hermitian. The maximum eigenvalue of this guy is equal to the spectral norm of B. So you have to check this. And if B is D1 by D2, then this is D1 plus D2 squared. Okay. Now, if you want to study Rademacher series with rectangular matrices, you just stick this map in. So here's how this works. So if B1 up to Bn are D1 by D2 matrices, and you're interested in a Rademacher series composed of these matrices, the probability that the spectral norm of Z exceeds T is equal to the probability that the maximum eigenvalue of H of Z exceeds T. And so we know that this is less than the dimension of that matrix, D1 plus D2, times the exponential of minus T squared over 2 sigma squared, where now sigma squared is the expectation of H of Z squared. Okay, well, what's that? Well, turns out that if you square this matrix, you get B star in the upper left block and B star B in the lower right block. And the norm of this matrix is the maximum of these two norms. So this gives you the expectation of Z star up here, the expectation of Z star Z down here, and in conclusion, this is the expectation of Z star in norm max with the expectation of Z star Z in norm, which is exactly the variance we saw in the Bernstein inequality. No, because of the expectation. They can average to very different things. Okay. And so even though it seems like the rectangular case might be somewhat different, it's really a formal consequence of the square case, of the symmetric case. And so you can prove all of these nice results for maximum eigenvalues and then get results for rectangular matrices for free. So very slick idea from operator theory. All right. Any last questions before we take another break? Yes?
It might be a very stupid question, but how does it relate to the theorem in the previous class?
Well, it's the same variance, isn't it?
So that's the same thing, right? But it's only about Rademacher.
Yeah.
The previous one.
So what would you need to do to convert this argument into a Bernstein inequality? So where was the difference? This is the assumptions on the summands, right? So we used the fact that the summands were Rademachers times matrices to prove a CGF bound. If you had some general random matrix that were zero mean and bounded, you'd have to use a different argument to get a different bound on the CGF. But you plug that in, you crank through the argument, it's just like the scalar case. You wind up with a Bernstein inequality instead.
But you had in the denominator, in the exponent, you had this funny expression.
Yeah.
So how does that enter?
It comes from having a different bound on the cumulant generating function, the log of the moment generating function. That's it. I mean, and then when you optimize over that parameter theta, it just gives you that, well, if you're clever, it gives you that form for the tail. Anything else?
So let me suggest we take a shorter break this time.
Okay.
Actually, like the 7.5, go to the bathroom, get your favorite beverage, take some deep breaths kind of thing, so we don't lose people on the tail end of the day.
10 push-ups.
10 push-ups.
And it will give Joel his last 30 minutes solid for moments, big moments.